Thanks again to Dr. Ray Boeche, who's with us the previous 2 hours. I mentioned earlier in the broadcast about an amazing thing that happened within the past 12 hours or so. The NASA OSIRIS-REx, the first U.S. mission to collect a sample from an asteroid, returned to Earth carrying materials from the asteroid Bennu. I mean, it's just astounding that this has happened, that they were able to pull this off. I can't wait to find out what stuff they brought back, what it looks like. NASA did release a picture. I'm looking at it right now of a bunch of the scientists standing around, and they're wearing protective suits looking at this stuff. And gosh, it just so happens we have our next guest works with NASA, is the editor and creator of one of NASA's most popular science websites, the Astronomy Picture of the Day. He's here to talk about an amazing new book called Faster Than Light. But heck, while he's here, we might as well ask him about this asteroid mission, too. My guest, Dr. Robert J. Nemiroff, comes up next. Here we go. Dr. Robert Nemiroff is a professor of physics at Michigan Technological University. He's quite proud of his award as an exceptional grad student mentor. He holds a Ph.D. from the University of Pennsylvania and became a fellow of the American Physical Society in 2022. Dr. Nemiroff is perhaps best known as the creator and editor for one of NASA's most popular science websites, the Astronomy Picture of the Day. In his spare time, he likes to play basketball, read and watch science fiction, and think about concepts in science that are both very simple and very strange. And boy, has he accomplished that in this new book, Faster Than Light, How Your Shadow Can Do It, But You Can't. Robert, welcome back to Coast to Coast.
Thank you. Thanks for having me back.
You know, it's only been 9 years, since you were a guest before, but it's long overdue. I wanted, before we jump into the main topic and talk about your book, I wanted to get your take on the current events. I mentioned a minute ago about this NASA spacecraft that returned to Earth carrying material retrieved from an asteroid. I mean, an asteroid. It's sci-fi, becomes real science. I would think it'd be a real proud moment for your friends and colleagues at NASA.
Yes. First of all, I'd like to say that I'm speaking as myself and not on behalf of NASA.
Oh, sure.
I think it's just tremendously exciting. Yes, the OSIRIS-REx spacecraft banged into a small asteroid a few football fields across and collected a sample and has jettisoned it, and it's just within the past 24 hours came down in the Utah desert. And so it's been retrieved. It's chased by helicopters. You might say that an object from outer space crashed into Earth, and on the way it was chased by helicopters and picked up and moved into a lab where we're going to study it. And that's exactly what happened. But it's not an alien spacecraft. It's something we put up there. And it's really exciting because it has most probably dust from this asteroid that was deposited there in the early solar system. And so we might learn more about the early solar system.
That's amazing. Well, it was alien to the asteroid, that's for sure. So, what? I mean, is it dust? Are we going to have rocks? Is there anything else? What does this material look like? Just like dust from our planet?
Well, again, I'm not an expert on this.
Right.
This is not my specialty. Is other areas of astrophysics, but I think it's a small rocks, dust. Yeah, it's not anything really large. They impacted. It's like the spacecraft put out an arm and then banged into the surface and loosened things that would come free. And then some of that fell into the spacecraft, a specific compartment in the spacecraft, and that closed up. And they think they have about a coffee cup size, maybe a little bit bigger than a coffee cup size of material, mostly not ground up because it ground it up, but it was just dust and rocks. And that capsule has been returned. And, it's very exciting. We're going to see if there was a lot of organic material in the early solar system, and maybe the seeds for life were out there. But also, asteroid Bennu, I understand, is a bit of a hazard risk in that it comes very close to the Earth every now and then.
Oh.
And so far as we can tell, in the near future, that won't happen. So nobody alive today has to worry about asteroid Bennu hitting us. And if it did hit us, it wouldn't destroy life on Earth. It's not as big as the asteroid that troubled the dinosaurs and killed off the dinosaurs, but it could cause some problems. And so it's best to study it and understand it. There's no real trajectory that we know that it will impact Earth. It will come very close. And if the more distant trajectory of the asteroid is not all that well known, so it could, in several thousand, maybe millions of years, impact the Earth. But we now have the ability NASA, humanity has the ability to impact asteroids like this with small objects and slightly change their trajectory. And so if we find that with future analysis that it might be hitting the Earth, we might be able to slightly nudge it so that it misses.
I don't mean to put you on the spot because this wasn't the topic you were here to talk about, but you're as close as I get to NASA tonight and happen to be on the show, so that's why I was asking the question. I just find it just astounding that we can shoot a rocket out at an asteroid that's hurtling through space, a small asteroid, intercept it, get some stuff, and come back. It's just astounding to me, you know.
Yes, it is amazing. We live in a futuristic world in many ways, and we have more spacecraft out exploring almost everything in the solar system. Every major planet has been visited, and now we're visiting lots of asteroids and even bringing them, little bits of them back to study. So we just don't have to see them through telescopes. We can actually study what it is they are.
I want to ask you about the James Webb Telescope because, I mean, you deal with the images or the photos of the day. I'm sure some of those must come from James Webb. Can you address what that means to NASA, to the world, to science? What's happened that you've seen from the James Webb that's amazed even you?
Okay, so the James Webb is a new big telescope. It's bigger than the Hubble Space Telescope, several times bigger. It co-orbits the sun with the Earth, and it sees some red light that we can see, but mostly into the infrared. So it sees red light, more red than humans can see. And so that's good because a lot of things emit light, like you and me, we emit light in the infrared much more than we do in the optical visible light that we're used to. And so when you see into the infrared light, you can see into dust clouds, and you can see parts of the early universe that you couldn't see before. So what we're seeing is images coming in of the insides of nebula that we didn't know, and we're seeing back to the early universe, parts of the early universe that we hadn't seen before. So we're figuring out how it is better that galaxies formed and planets formed. And yeah, because of the size of the telescope, we're just getting some tremendously detailed images. So it's visually just amazing, some of the things that came back in. One thing I was surprised about is that Webb is being pointed just at objects inside our solar system. So there's a picture of Jupiter that's tremendously detailed that we've been able to feature. And you can see things in the infrared. You can see actually Saturn is famous for having rings. Well, Jupiter has some rings, and they glow a bit in the infrared. So we can see them. And we can see aurora on Jupiter, and we can see the interaction between Jupiter's aurora and its moon Io. So we're able to study that, the interaction of that in greater detail. But Webb is just doing great things. It's bigger than Hubble. Hubble complements it in some way. Hubble can see into the ultraviolet, which is light more blue than we can see. And there are advantages to being able to see into the ultraviolet. And Hubble sees the entire visual range, too. So the two telescopes actually can complement each other in many ways. But we've never had a telescope like Webb before, so it's very exciting.
Yeah, I mean, do you get a feed of the photos that come out of Webb, or you get your pick of those things for your feature, the astronomy photo of the day?
Well, we don't have special inside information from that. So we see the images that everyone else that NASA releases. NASA is a very transparent organization. When they take images of things, usually within a day or two, it's released into the public. So we see that too. But one thing we do on the Astronomy Picture today is, since we're astrophysicists, we can explain it and we can put it in context in a very short explanation that's hyperlinked into the web. So we can pick out some of the images that are most visually stimulating. We can pick out some of the images that have the most science in them, and we can tell people very clearly in very short text what it is they're seeing and why it's important.
The kind of information that comes your way every day, it would seem so overwhelming to me, and I say it in the context of, Webb. It sees so far out if you target something way far out, and it's like the march of science, the march of knowledge is a lesson in increasing humility for we humans. How small we become, the more we learn about how big everything else is. Agree?
Yeah. Humanity keeps passing. As technology increases, humanity is able to do more and more. And sometimes you live in a part of humanity where things didn't really progress very much. So you pretty much study what's been known. But we live in a time when there's spacecraft that go out into the solar system, and we can build telescopes that can see far out into the universe. So we are just seeing, we're like open field running. There's all this great stuff that's coming in. We live in a very fortunate era, a golden age of exploring the universe and seeing the universe. More than 100 years ago or so, we thought our galaxy was pretty much the whole universe. But now we know that all those little spiral nebulae and all these other things are actually galaxies like our own. And we can see the outer universe expanding. And so even just in the past 100 years, there's been revolution after revolution of humanity's understanding of what universe is. And just seeing all these amazing things out there. And the latest chapters of that, well, there was Hubble, and now there's Webb. But there's also other little telescopes that fill in little niches that are important too. And little spacecraft that go out like OSIRIS-REx and capture little bits and coming back. And 100 years ago, this would be almost inconceivable. Actually, some of the science fiction writers of the day actually sort of foresaw that some of this might happen, but the average person on the street would have no reason to think that, and now it's come true.
A century or more ago, there were scientists on Earth, who thought there was life on Mars. They saw the canals and figured they had been engineered. And then more recently, people figured our solar system must be dead. There's no chance any life exists. The more we learn about our own solar system, the more possibilities of some kind of life might be out there. These frozen moons and maybe ancient microscopic life still on Mars. It's a really exciting time, even in our own little neck of the galactic woods here.
Yes, it could be the next major milestone for humanity is discovering extraterrestrial life. And I know a lot of people like me think that it must be out there somewhere, and the big question is, how will we discover it? And so I was actually involved in organizing a debate a few years ago as to whether we would probably discover extraterrestrial life through what we call biosignatures, meaning that we would find something on Mars, something that landed on Mars would find something that would indicate that life existed there in the past, and or we could find it through technosignatures. We would get some radio broadcast that would obviously indicate that there was extraterrestrial life out there, and or we would see some kind of technology out there that we obviously didn't develop. And so there's sort of a battle in the community now between how is it that we will discover extraterrestrial life? Will it be through biosignatures or will it be through technosignatures? But right now, every year that goes by, we keep expanding the frontier further and further, and yet we have no clear evidence of extraterrestrial life that is confirmed yet. And so it's exciting it's like sitting on the edge of your chair wondering which it will be. And we keep, with Webb telescope, Webb is looking at exoplanets, planets orbiting other solar systems. We're looking for biomarkers in those exoplanets. Maybe there's something that clearly tells us there's life on some of these exoplanets, or on Mars, maybe something will be found that is a clear signature of that. Or we're also listening in more and better ways into the solar system with radio telescopes and trying to listen in different places. And so far, we haven't heard anything that clearly and reproducibly indicative of extraterrestrial life. But it is possibly the next major leap of mankind to understand that we're not alone in the universe.
Yeah, it's a very exciting possibility. I hope it happens in my lifetime. And I promise we're not going to dwell too much longer on this. I want to jump into talking about your book and the ideas therein. But just one last question on this. I mean, in my line of work, we cover a lot of really what you'd call pretty weird stuff, UFOs and things like that on this program. I'm not going to sort of pin you into that area, but could you share...
on coast to coast? You're...
Could you share with me your thoughts on what happens, how humans, our civilization, reacts to the discovery and confirmation of ET life, even microscopic ancient life on Mars that's no longer there? How does that change things? Why would that be such a major development?
Wow. So that's a really great question. I haven't really put too much thought into it. It's like you kept trying to do something, and then when you finally do something, it's like, oh, now what?
Now what?
I think humanity would take it in stride. I think a lot of humanity does believe that we're not alone in the universe, and there would be a lot of curiosity as to what is it that's out there. Okay, now they found it. What else is it that's like that? What? So it was discovered. Let's say a biosignature was discovered on a moon of Jupiter. What is that? Are there fish down there? Are there frozen fish orbiting Jupiter that we just missed because they're so small? How do these things live? How do they see? Are we related? Are they DNA like we're DNA? Are they based on something else? Is there? And then can you extrapolate on that? Do you expect is this just a solar system thing? Is this solar system just lucky to have a DNA-based life, or is this something that you can see out in the universe? For instance, if you were to detect DNA-based life out of an exoplanet, out of our solar system, that would indicate that the DNA is not so unusual. This way of reproducing ourselves is not so unusual. Or maybe it's something completely different. And I think it would just create in humanity a lot of curiosity as to how this happened and what are the future implications. Is there lots of life out there? Is there other intelligent life out there? I think it would be like going through a door of understanding and finding yourself in a new space and just wondering what it is that's in this space.
Yeah, it'd be exciting just to figure out if panspermia is real, that life came to Earth from somewhere else on an asteroid, on a comet, something like that. And if so, whether there's a common denominator between life here and life out there.
Yes, exactly. These are questions that would be asked in greater detail than ever before, were we, and hopefully when we discover extraterrestrial life.
About your book. So, look, a lot of people in my line of work, journalists, they chose this profession because it allowed us to avoid math in part, because math is hard. If you had been teaching physics when I was back in college, I might have paid closer attention because the book is so much fun. There are so many of the subjects that you cover in this book, Faster Than Light, How Your Shadow Can Do It, But You Can't. It goes over the heads of regular lunkheads like me, but you seem to have set out to make it fun for physics students and clear enough for the general public to follow along. Was that the goal?
Yes, it's a bunch of interesting concepts. So what I tried to do is there's a little bit of math, but I tried to stay away from the math. As I say there, a lot of science progresses with data. So a lot of information is brought in, like the sample from Osiris Rex is going to be analyzed, and we'll have all this data. A lot of things. So humanity has created math to help us explain the data in some way. Here we're going to fit this data, and here's the relationship between the data. But at a higher level, in my view, higher than math is concept, and everybody can understand some of the really cool concepts. So in my book, I try to hand wave across the math and acknowledge the data, but not really get into much of the data at all, but try to focus on the really cool concepts that are behind the greatest speed limit there is, which is the speed of light, because the speed of light is just a tremendously interesting speed limit, and it creates things like time dilation and time travel, certainly into the future, and strange little paradoxes that come up, but it's not impossible to understand without math and data, and without math in particular. So I tried
retrocausality. We're going to jump into retrocausality. We're talking with Dr. Robert Nemiroff about Faster Than Light, fascinating book. We're going to jump right into the heart of it when we come back. Faster Than Light, How Your Shadow Can Do It, But You Can't is the most hilarious science book I've ever read. Robert J. Nemiroff is the guy who wrote it, and man, it was a fun read. There's some, just to give you a context, on the back cover, there are some historical blurbs written for the book. This one comes from Aristotle in 330 BC. Since light has infinite speed, this book is useless. Or a quote from U. Everett III. In some versions of the universe, I do not supply a blurb for this book. If you knew who U. Everett was and what he proposed, then you'd get the humor of that. When we come back, we're going to jump into the heart of the book. Is anything able to travel faster than the speed of light? We're going to find out. Robert Nemiroff, Faster Than Light, How Your Shadow Can Do It, But You Can't, is really good. Is this material taken from lectures that you've given, or you pulled it together over the years?
Well, I've always had an interest. For many, many years, I had an interest, and I've actually published on some of the strange aspects in science journals, some of the strange aspects that shadows and laser spots can do when they go faster than light, because even the physics community, once they see the logic, they don't disagree with it, but they're unaware of it. So if you were to go and speak to someone you know that's versed in physics, they would say, oh, no, that can't happen. But once you explain to them the logic of how it does happen, they'll say, oh, yeah, that's kind of cool. And it is. It's really strange. It's one of these untold stories out there that there's this whole universe of things that happen faster than light that we don't know. For instance, when you turn on a room light, the room, at first the room is completely dark, and after a second, for sure, the room's completely illuminated. Well, the boundary between dark and light moves across the wall faster than light. So if you could see at those speeds, you would be able to see a much different universe. You would see lots of things moving faster than light all the time. And so one of the reasons why we can't do it, why we can't see it, is because our brains and minds are so slow, that was me, that it just doesn't come through. But now with modern technology, we can have rapid time-lapse photography and see these things.
You drop a lot of really cool historical facts in the book about how, the understanding of the speed of light, how it developed and changed over the centuries. Maybe let's start there. I mean, tell us a little bit about, and what you cover in the book, about the first folks to try to measure the speed of light. Is it Galileo, or even before that? People
have been speculating about the speed of light since in most of recorded history. For instance, as you noted, let's see, Aristotle and Euclid back in the BC times, they sort of thought that what happens is light doesn't come from an object, from a star or from a light to you. Light goes from your eye to the object you're seeing. And for most of human history, that's the way humans thought it was. Every now and then someone would say, no, wait, I think it's the other way, but that was not what most people believed. And it was only around 1000 A.D. that it was more and more realized that no, that's not the way it is. Light actually goes from something and comes to us. And that's when, so back in the BC time, people thought, well, the speed of light must be infinite, because when your eyes are closed, you don't see something. And then when you open your eyes, then light goes out from your eyes, and you can see things, even stars that are far away. Therefore, the speed of light must be effectively infinite. But once people realized that light was coming from other things into their eye, then people realized, well, maybe it's not infinite. Maybe it's got some speed. But for many years, they just couldn't measure it. It was so fast. As I like to tell my students, there's really only three numbers in conceptual astrophysics. One is infinity, which means it was really too fast or too big to measure. One is 1, means that we measured it, it's one of those. And the other is 0. The third number in astrophysics is 0, because it means it's too small to measure. It might be there, we don't know what size, but it's effectively 0. So for a lot of human history, the speed of light was infinite because it was just too fast to measure. We couldn't do it. So people like Galileo, they tried to do it. They would go to mountaintops or hilltops, and then someone else would be in another hilltop, and they had lanterns, and they had black things they could put over the lanterns. And so they would make deals. Say, you and your hilltop, when you see me uncover my lantern, you uncover your lantern. And I'll count the amount of seconds it takes before I can see your lantern. And so Galileo did this, and other people did this, and they found out, well, it's about a second. No, it's about 2 seconds. No, it's about half a second. And they realized they weren't getting a consistent answer. And Galileo realized that, no, I just don't believe it. If it was infinitely fast, what we're really measuring is how long it takes to uncover the lanterns. We're not really measuring anything to do with the speed of light. So many efforts to measure the super fast speed of light just failed, until suddenly in the 1600s, someone who was not famous just happened to be doing something that some people didn't think would be all that interesting, and they got a result that they didn't understand. but that result was a door. That door that we went through is the finite speed of light. And that person was Ole Romer. And Ole Romer, what they were doing is they were just watching the moons of Jupiter. And the moons of Jupiter, particularly Io, would go behind Jupiter, go in front of Jupiter. And Romer noticed there was just something odd about the timing of these eclipses. And the eclipses would take longer in some circumstances and shorter in other circumstances, and it just didn't seem to make sense. And so meanwhile, on the other people on the next hill trying to uncover lanterns, but Romer was saying, hey, wait a minute, can you understand this? And the answer, it turns out, that Ole Romer was actually the first to discover the finite speed of light and to measure it within a small fraction, not super accurately, but relatively accurately, like we know it today. So the discovery was just a bit of a surprise, and it advanced human knowledge in a great way by just a sort of a serendipitous result.
You write a couple of different places in the book about there being more than one speed of light. Can you explain that?
Yes. So now we know, in modern science, we know a lot about the speed of light. And we know that the speed of light so when you look through water, the speed of light in water is not the same as the speed of light in air or in vacuum. Speed of light through air and vacuum are actually very similar. It's a very small fractional percentage difference between those. But in water, it's like a third slower. But there's different even kinds of light. We now know things about the way light works, and there's phases, and there's something called the group velocity. The group velocity is more or less how long it would take light to go from you to a mirror to bounce back. If you measure that speed, which we can now do with great accuracy, you're measuring the group velocity of light. There's also things called the phase velocity, whereas if you measure how much light is deflected, but that's not all that important, really. It's important for understanding the details of physics and how things work. But in terms of the conceptual speed of light, we now know that the speed of light in glass is different than the speed of light in water. And the speed of light in water is different than the speed of light in air, which is slightly different than the speed of light in vacuum. And the fastest that we know that anything can pass you by is the speed of light in vacuum. And so we call that the speed of light. But it really means fastest speed that we know of in terms of something that has energy and mass can go.
I understand the speed of light is not just an exercise in and of itself. I mean, it helps to understand the much bigger picture of the universe we live in and the nature of reality, right?
Yeah, so light is just a fundamental thing. It's one of the it used to dominate the universe. The photons that make up light used to have the most energy in the universe. But now the universe has evolved. The light has become less comparatively energetic, whereas mass and now something called dark energy have not diluted like light. So now light there's like billions of pieces of photons for every atom that we know of. But still, the amount of energy in light has gone down a lot. And so now light isn't most useful for its mass and its energy. The energy it has is most useful for what it can tell us because it's crossed the universe from far away. And so when we look at it near and far, we can try to decode what it is. Light was created someplace, light was reflected from someplace, light was emitted from someplace, and we piece together the universe from the light we see, pretty much.
You have some fun exercises in the book. There's no way we can cover all of them, but one of them early in the book is an aside where the title is "Nothing Can Go Faster Than Light," which is, I think, probably the general assumption that most of us non-scientists would suggest. But you say that if you were to head into the local university and ask a random physics student if anything or if shadows could go faster than light, you're probably going to get an answer, no, nothing could go faster than light. But they'd be wrong, right?
Yes, they would be wrong. So it's an amazing thing. I've given talks, and I've had good physicists in the audience object, saying, "Oh no, that can't happen." And then when I try to detail it, they don't even want to let me continue. So we get into an awkward part where I say, "Oh no," but then I speak at another university that has just as prestigious scientists, and they love it. They say, "Oh yeah, this is really interesting. This is really great." So, yeah, if you were to go into this department, you might find people there who would seem to disagree with this. But unless, what you can do is you can tell them to look up my articles, not only my articles, there are other articles, and to read this book. And it makes it very clear And it's been measured in the lab, too, that shadows and laser spots and illumination fronts, like when you turn on a light in a room, they all can move, and they do move faster than light.
And you wrote that you've submitted papers to recognized physics journals and had them rejected because the editors say, oh, no, there's no way, this paper's flawed because nothing can go faster than light. They're wrong.
Yes, that has happened, too. So what happens is we have editors that know. So when you send in, you do some research, you send it into a journal. So the journal, you send it into the editor, signs an editor. Then the editor has what's called referees. You can picture their scientists that sit around with stripes on them, and they advise the editor as to whether this piece of science writing that was submitted to the journal should be published or not. Many things submitted to journals are not published because the editor, on advice of the referee, usually says, oh, no. So we now know for some journals, some editors are clued in and they understand what we're doing and that this is correct. But if we get the wrong editor and the wrong editor submits it to the wrong referee, then we just get back a rote rejection, which we know to try to push past. We ask that editor send to a different referee, or we ask that another editor take over. And so since we are able to publish our stuff, that is a successful tactic. But you're right. We've gotten just, back an immediate thing saying, oh, no, this can't be right, because someone hasn't thought it through. They remember some adage that says nothing can go faster than light, which is nothing with mass can pass you faster than light. So far as we know, we don't have any examples of that. But shadows can go, laser spots can go, things can go, and these things can be very, very interesting and tell us things about the universe that we didn't know before.
Yeah, you have one experiment in the book that where you point a laser pointer at the moon, and it can go. You can whip it around, and it could go faster than the speed of light. Correct?
Yeah. So one of my favorite thought experiments, and there's a lot of conceptual thought experiments in the book, is let's say you're here on Earth, and let's say there was this big dome out 1 light year away. So if it's 1 light year away, it takes light a whole year to get there. So now you have your laser pointer. So you take your laser pointer and you point it at one spot in the dome. And even though you pointed it there, it's going to take a year for light to get there. But then in 1 second, you take your laser pointer and you shift it around to 180 degrees around to the other side of the dome. So after a year that it takes light to get there, the laser spot will go all the way around that dome in a second. But that dome has a circumference greater than a light year, so that spot is moving greater than a light year in a second, which means the spot has a superluminal speed. Now, there's no information being created on the dome that's moving on the dome faster than light. The laser spot is the superposition of unrelated photons that are hitting at different places, and so that is what is appearing to move faster than light. But yes, these things. We don't have a dome out at 1 light year. But these thought experiments are very clear demonstrations that laser spots can move. So if you take your laser spot, maybe we don't have a dome a light year away. What we do have is things that are closer. So the moon, if you just try your local wall and you take your laser pointer and you sweep it around the wall, you can't move your arm fast enough to make it go faster than light, unfortunately. But the moon is far enough away so that if you take your laser pointer and you sweep it past the moon at a reasonable speed, not too fast, that laser spot, if you could see it, would move faster than light across the moon.
You have a chapter that deals with how to make a magnetic field move faster than light. So is there a simple answer to that, a simple explanation that we would understand?
Well, that's a tough one. Because,
okay.
But the magnetic field lines are actually not something you can grab onto. They're conceptual lines of that has something to do with magnetism. So we draw them in, and then when the magnetism changes, you turn a magnet or something like that. Yeah, these magnetic field lines can move faster than light. That's very clear. But it's not that easy to explain. So I did go to some effort in the book to do it, but I don't know if that would work here in the coast-to-coast format very well.
You do touch on here and there the differences between relativity and quantum mechanics, and try as I might to get my head around it, I just can't do it. But it seems to be a lot of what quantum mechanics concludes to be real and true is at odds with what we think of as relativity. I don't know how they coexist, but they do, right?
Yeah, so they are not we don't always know how they interact, and we're sometimes surprised, but quantum mechanics does not contradict special relativity. In fact, there are types of quantum mechanics, quantum electrodynamics, and things like that incorporate special relativity into them. The classic quantum mechanics, the Schrödinger equation, it's called, that can be brought into conflict with the concept of special relativity. But physicists do know that special relativity is right and that it does fit into quantum mechanics. But that doesn't mean there's some really strange quantum mechanics experiments out there that it appears that information is being transferred faster than light, but it is not. When it's looked at in very detail, it's just the appearance that it is. It's not really going faster than light. And how that is just absolutely fascinating. How it seems like something on one side and something far away, they seem like they know about each other, but they're not communicating. And so if you look at the details of it, which I try to explain in some of the chapters in my book, you can see that there's no real communication going on there. There's correlation, which we don't understand why there's correlation, but there's no communication.
There's some fun stuff in here that we're going to jump into in the next segment after this break. Retrocausality. Can the future influence the present, for example? Can you send information back from the future to the past? A lot of fun stuff in the book that we're going to be jumping into in the next segment. Stick around with my guest, Dr. Robert Nemiroff. Faster than light, how your shadow can do it, but you can't. Lots more to come here on Coast to Coast.